Hello friends, welcome to CEC live lectures. Dear friends, with our ongoing series on natural products and spectroscopy, today we are going to talk on mass spectroscopy and spectroscopy problems. For the discussion on the topic, we have with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dr. Vandana has immense experience and she is contributing in the area of academics persistently and continuously. She makes efforts so that she could make higher education easier, and through the live platform her efforts are recognized and these efforts are viewed by you all. Dear friends, let's welcome our guest Dr. Vandana and let's try to understand today's topic in detail, that is mass spectroscopy and spectroscopy problems. Hello ma'am, welcome to the lecture.
Thank you so much ma'am. Hello viewers, in this series we have discussed various lectures regarding spectroscopy, like we have discussed in detail about UV visible spectroscopy. We have discussed in detail NMR spectroscopy, and then we have discussed IR spectroscopy. We have discussed mass spectroscopy also, and in today's lecture we will take some organic molecules, their fragmentation patterns, how they fragmented and give different fragments. You know, because in mass spectroscopy we observe the positive species in mass spectrum, and through which we have an idea about the molecular formula of a compound and the different fragment, or you can say different constituent of a compound. So we can say mass spectroscopy is a unique technique to identify a unknown compound and to compare the compounds, to compare their identity, to know the unknown compound, or we can say impurity of a compound. And in the next part of this lecture we will discuss about in detail about the spectroscopic problem. What is spectroscopic problems? That is how can we identify by applying all these knowledge, that is by applying the UV visible, IR, NMR and mass spectra, how these helps us to identify the unknown compound or to compare the compounds or to identify the impurity of a compound. So let us first discuss about the remaining compounds, how to identify the different fragmentation pattern of halogen compounds. The molecular ion abundance of a particular alkyl halide increases as the electronegativity of halogen substituent decreases. The relative abundance of the molecular ion decreases with increase in chain length and increase in branching. Compounds containing chlorine and bromine show characteristic isotopic peaks, and you can observe M plus 2 peak, which is 1/3 of intensity of the parent ion. In monochromo compound, it shows M plus 2 peak, which is of the same intensity as compared to the parent ion. When we compare the another halogen atom, in the parent ion the charge resides on the halogen atom. Important fragmentation mode is alpha cleavage with the charge retention by the halogen containing fragment. Another mode leads to the loss of halide radical. Here you can see the preferred fragmentation halogen compounds will takes place. You can see here this is the alpha carbon, the fragmentation followed by this bond, and you will get this kind of charge species, and you can see that a halogen atom will carry this charge, so that it will be analyzed by mass spectrum. You should be noted that charge species will be identified by mass spectrum, not the neutral molecules. And another fragmentation pattern for this particular kind of structure, you can see this is the molecular ion of a molecule. Now these are the different fragmentation pattern. Here you can see this kind of cation, one more cation is there and another cation is there, and this kind of fragmentation is also possible. Here you can see this is a cyclic molecule which carries a halogen atom. This is the mass spectrum of 1-bromohexane, and here you can see we will observe the what we can see over here, the isotopic bromine 79 and 80 when also observed in the same intensity. You can see the relative abundance will be the same. If you observe in any spectrum, you can immediately have an idea that bromo compound should be there. This is the another molecule and it shows the different fragmentation pattern like this. This is the molecule having mass to charge ratio 135, 137 also, and by elimination of this kind of radical you will get this kind of cation. It has in with the resonating structure because it is rearranges to give this kind of carbocation because it is more stable as compared to this primary. This is secondary carbocation. So less stable carbocation will immediately rearranges to more stable carbocation itself. Another fragmentation you can see over here, it will absorb at 107 and 109. Here these are due to the isotopic bromide ion. What I am saying over here 135 and 137, here also 107 and 109. So immediately you will have an idea that bromo compound is there. Another fragmentation pattern is also there. Now amines. In amines, if molecular ion is formed at the odd mass number, then the molecule carries an odd number of nitrogen atom. The molecular ion peak in monoamines is formed in very small abundance and is undetectable in long chain or branch chain amines. For primary amines, the base peak is formed due to this kind of fragment which is observed at 30 at a value of 30 mass to charge ratio, and it will result from alpha cleavage of the molecular ion. This peak is a good but not conclusive evidence for a straight chain primary amine. The fragmentation of the parent ion formed from secondary and tertiary amines leads to a number of peaks 30 at a value of 44, 58, 72 and so on. The parent ion may lose an alkene to form a fragment ion. So this kind of fragmentation also possible in case of amines. Loss of largest branch from alpha carbon will be preferred. When R or R dash is H, then M-1 signal will form. The same type of cleavage is also noted in case of alcohols. That is why we told you this is not the only significant for amines. This effect is more pronounced due to the better resonance stabilization of fragment ion, as the electronegativity of the nitrogen is less as compared to the oxygen. In higher aliphatic alkyl amines, beta cleavage is not very significant, alpha cleavage is sometimes preferred. So here you can see what kind of fragmentation followed over here by the elimination of this kind of radical. You will get, here you can see R2 is greater than R1 or R. Greater than means it is more branched alkyl group than R1, or R1 is more branched group than R. So we have to see the highly branched part will cleaved first as far as the fragmentation is concerned. So we will get this kind of fragment ion which is in resonance with this kind of cation. Here you can see the mass spectrum of ethylamine, that is CH3CH2NH2, and you can see the significant peak at 44, 45. This is the molecular ion peak, and this is due to the CH2 double bond NH2, 44. Mass spectrum of ethylamine, the molecular ion peak we have observed at 45. The alpha cleavage results in the formation of this, and it will gives you a base peak. Remember, base peak is very important for any kind of mass spectrum. The parent ion loses a hydrogen radical. This you can see over here how the cleavage of hydrogen atom took place over this nitrogen plus, and you will get this kind of cation at a value of 44. In amines, a hydrogen radical is lost from the parent ion to give M-1 peak, that is -1 from the molecular ion peak. Another amines, that is aromatic amines. In aromatic amines, a parent ion is formed, loss of 1 electron from the lone pair present on the nitrogen atom. The elimination of hydrogen radical and hydrogen cyanide molecule are very common from the parent ion. Thus, in primary aromatic amine, you will observe these kind of significant signals, that is M-1 and M-27. The elimination of 27 mass units gives a signal due to the cyclopentadienyl cation. For N-alkyl amines, alpha cleavage of the alkyl group will be preferred. Now, nitro compounds. The molecular ion peak in aliphatic nitro compound is usually absent. So, you have to see in which compounds molecular ion will be absent. It will give you immediately idea that particular compound cannot be there. But it is prominent in aromatic compounds. In aliphatic compounds, the signals due to, you can see NO plus and NO2 plus, nitrosonium ion and nitronium ion are usually observed. In aromatic nitro compound, the signals for nitrosonium ion, nitro ion and M minus NO, M minus NO2, that is a molecular ion will leave this molecule NO leave are commonly observed and minus NO2. If a hydrogen containing group is also present ortho to the nitro group, then MOH, M minus OH peak is also observed. For aromatic nitro compounds, the molecular ion peak appears at odd mass number. For one nitrogen atom, we have already discussed it, and is fairly strong. Also, strong characteristic peaks are observed by the elimination of nitro radical, and also nitrosonium radical is lost, forming phenoxycation. Here you can see the fragmentation pattern of nitrobenzene. This is nitrobenzene, and if we say more precisely, it is the molecular ion of nitrobenzene. And you know how the molecular ion get formed by the nitrobenzene? By the bombardment of high energy electrons. Now you can see by the rearrangement we will have this kind of a structure. That is, here you can see this is attached with the nitrogen atom, and here you can see the difference, it is attached to with the oxygen atom. So these are the rearrangement structures. Now by the elimination of this NO2 radical, you will get this kind of cation, and by the removal of this C2H2 you will get this kind of cation, that is C4H3 plus. And again from this molecule you will get this kind of possibility, that is NO. With the removal of NO you will get this kind of cation, and here by the removal of this carbon monoxide you will get this kind of molecule, that is cyclopentadienyl cation. When a substituent is present in meta or para position, the fragmentation modes are similar to those as observed in nitrobenzene. So no differences there, but when the substituent is present in the ortho position, then it interacts with the nitro group. Here you can see the nitro group is present in ortho position with respect to this group, that is methyl group. Here you can see a different fragmentation pattern will observe over here. By the removal of this kind of radical, we will get this kind of molecule. Here cyclization forms, and with the removal of this carbon monoxide, you will get this kind of cation at a value of 92. So you can easily confirm whether nitro group present in ortho position or not by the observation of these kind of significant peak in mass spectrum. Now aliphatic nitriles, you know what are nitriles? RCN, that is R group is aliphatic over here. The molecular ion peak of aliphatic nitrile is weak or may be absent. A weak but diagnostically useful M-1 peak is observed by loss of a alpha hydrogen atom to form a stable ion. The base peak of straight chain nitriles between C4 and C9 is at the value of 41, and this peak is due to the ion resulting from hydrogen rearrangement in a 6-member transition state. How? You can see from here. The base peak of straight chain nitriles between C4 and C9 is 41, as I told you. This peak is due to the ion resulting from 6-member transition state. So here you can see what kind of preferred fragmentation over here. You can see this is a loss of hydrogen radical. You will get this kind of cation, and which is having in a rearrangement, or we can see resonating structure. One more resonating structure is over here when the positive charge is on carbon atom, not on the nitrogen atom. A peak at a value of 97 is a characteristic and intense in straight chain nitriles C8 and higher. Here you can see this kind of transition state will form and we will get this kind of cation by the cyclization. Here you can see how the rearrangement took place, how the bond cleavage, and this bond will cleave from here at this position, and a new bond can be formed over here, that is cyclization took place, and you will get this kind of molecule or this kind of charge species as a value of 97. So we have discussed possibly all the functional group, all the compounds, not only functional group but the nitro compounds as well, aliphatic nitrite as well as the preferred fragmentation pattern for different kind of compound. So when you going to interpret any mass spectra, you should keep in mind first of all that the molecular ion peak in a particular compound is prominent or not, it is less abundance or high abundance. Immediately you will have idea. For halogen compounds, you have seen that if bromo compound is there, the isotopic peaks will observe with the same relative abundance. If chloro compound is there, then you will have the two signals 1:3 ratio. So you will immediately have an idea which compound should be there, can be there. Then you should go to the fragmentation pattern. We have discussed all the compounds and their preferred fragmentation pattern for a particular compounds. So this was about the mass spectroscopy, and we have discussed all four important spectroscopy for the elucidation of organic compounds. How can you interpret the organic compounds with the help of this? Now in the coming slides I am going to discuss how can you solve a problem if you have all kind of data, that is you have UV visible data in which you can have the lambda maximum of a particular peak, you have E maximum, that the epsilon maximum, and in IR you will have all kind of data. So how will you interpret to solve a problem? Let us discuss it. First of all, I want to tell you how can you calculate or have an idea from the data, how can you calculate the double bond or ring equivalents. As when you are going to analyze the presence of unsaturation or saturation in a compound, you will treat your organic compound with the bromine water or KMnO4 solution in the same way. From the spectroscopic technique, we also can have an idea how can we calculate double bond or ring equivalents. If the molecular formula of a compound is given, then number of double bonds or ring equivalents can be easily calculated. We will discuss all kind of compounds. The number of double bond equivalents from various types of compound with the given molecular formula can be determined as follows. Number one, how can we calculate? If the compound is a hydrocarbon, only carbon and hydrogen there, then we can calculate by this formula, that is x plus 1, x is the value of number of carbon and y is the number of hydrogen. You can calculate by this formula. Consider a molecular formula C6H6 and the number of double bond equivalent in it 6 plus 1 minus 6 by 2, that is 4. Some possible structure consistent with the given molecular formula. Here is 3 double bonds and 1 ring, and another molecule can possible with this molecular formula. Here you can see 2 double bonds and 1 triple bond. A triple bond may be regarded as equivalent to 2 double bonds. The presence of a triple bond, that is C triple bond C, C triple bond N in case of cyanide, in case of acetylene or alkynes, can be easily recognized from the infrared spectroscopic data. Type 2, if the compound contains one or more divalent atom, that is if we contain sulfur or oxygen, what should be the formula to calculate the double bond equivalents? In addition to the elements, that is carbon and hydrogen, then we can calculate by this formula. Here CXHYOZ, that is Z represents the number of oxygen atom, and this will be the formula. Here is the example. A problem is here. Find out the double bond or ring equivalents for the compound which is having the molecular formula C3H8O3. The molecular formula, the number of double bond equivalent you can calculate this way, 8 by 2. So double bond equivalent will be 0. For this particular molecular formula C6H6O2, and you can calculate by putting these values in a formula and you will get number 4. Third, if molecular formula of the compound contains some monovalent elements, we have discussed divalent. Now if halogen atom like chlorine, bromine or iodine, then for calculating the double bond equivalents in its structure formula, each halogen atom may be considered as a hydrogen atom. If compound with molecular formula, if we say this is the hydrogen formula, then CXHYXZ, the number of double bond can be calculated in this way, X plus 1, Y plus Z by 2, and you can see this is the example. This is the molecular formula of a compound C10H7Br. So in this way you can calculate this by putting all these values, 10 plus 1, 7 plus 1, because bromine atom is 1. So you can calculate the number of double bond equivalents in the compound. If the compound contains nitrogen atom or some trivalent phosphorus atom, then the number of trivalent atoms are subtracted from the number of hydrogen atom present in the molecular formula. If a compound having general formula CXH6NZ, here 6 should not be there, it should be Y. The number of double bond equivalents can be calculated in this way, X plus 1 minus Y by 2, and the number of trivalent nitrogen should be eliminated by Y. Here is a problem. Calculate the number of double bond or ring equivalent in the compounds with the molecular formula. These are the formulas. First formula is C12H12N2. For this we can calculate, this is the value of X, Y, we have to deduct minus 2, so you will get the value of finally 8. The number of double bond equivalent for the another formula, that is C6H8O3N2. So in this way you can calculate. In case phosphorus atom is pentavalent, then corresponding to each phosphorus atom, 3 hydrogen atoms are subtracted from the number of hydrogen atoms given in the molecular formula for calculating double bond equivalents. The number of nitrogen atoms if present in an organic compound must be odd, then molecular formula must be odd. So in this way, for different compounds, if it is containing sulfur, if it is containing oxygen, if it is containing divalent sulfur and oxygen, and monovalent, that is halogen atom, chloride, bromide, iodide, or trivalent or pentavalent, we have discussed how can you calculate, how can you have an idea what should be the possibility of compound from the different spectroscopic data. Now you can see this is a combined problem, organic compound with molecular mass. So you can see molecular mass is given 58 and is transparent above 200 nanometer in its ultraviolet visible spectrum. That is, this data is for UV visible calculation. Another supplementary data is there. In infrared, the absorption bands formed are at a value of 2941 to 2857 centimeter inwards. Another peak is there, that is 1458 centimeter inwards, and you can see the M, and in NMR spectrum, 2 singlets are formed. One is triplet at a value of 5.25 tau. You know how can we calculate the absorption shift, that is delta 10 minus tau, and here you can see coupling constant also, J is equal to 7.1 CPS cycle per second, 29.4 squares, and another peak is there as a quintet at a value of 7.25 tau, and J value for this particular peak is 7.1 CPS and 14.6 squares. So this is the problem, and here you can see all 3 kinds of data are here: UV visible spectrum, IR spectrum, and NMR spectrum. So we will start one by one. The formation of a triplet, 5.25 triplet, and a quintet is this, can be explained in this ratio with the help of this coupling constant, that is 14 multiplied by 2 can have a nearby 29. So we can explain this. If you understand this, I will repeat it. The formation of triplet at this value and quintet at this value can be in the ratio of 2:1 with the help of J value, that is 14.6. If we multiply by 2, you will get this point. So these 2 peaks are in the ratio of 2:1, and can be explained if two CH2 groups from one set and another CH2 group from another set of protons. It means that 4 protons are exactly in the same environment, while 2 protons, that is CH2, are in different environment. Because if you remember the splitting pattern, for CH2 we will get triplet, and for CH2 there are total 4 protons, so we will get quintet. 4 plus 1 quintet we will get. So these should be the parts of the structure. This is for your viewers. If you want to solve a problem, first of all you need to go through all kind of spectroscopy, that is UV visible, IR, NMR and mass. Then only you will be able to solve this problem, otherwise you will have some difficulty. So it amounts to, if we calculate the molecular formula of these two signets, it will comes out to 42 mass units, and the remaining 10 mass units corresponding to an oxygen atom. So considering the multiplicity, you know what is multiplicity? When we talking about the fragmentation pattern, if you don't understand, you go back to the NMR spectroscopy and see the splitting pattern, and this is the multiplicity of signals. And the structure of the compound can be written as like this: the triplet of A protons at a low field. Now we have to see the field, whether they are at low field or high field, confirms that oxygen is directly linked to two CH2 groups. Oxygen atom causes de-shielding of their protons, and the same to which proton with different chemical shifts are linked are adjacent carbon atom. And from NMR spectra, this value 2941 to 2857 shows the CH stretching, while at a value of 1458 centimeter inverse shows carbon single bond carbon stretching. So in this way you will able to calculate, or you will able to elucidate what should be the structure for this kind of problem. So hope you understood this, key how will you proceed to calculate or to elucidate or to identify what kind of compound should be there. You have to keep all the minds together in a that what is the molecular formula given, what are the values of ultraviolet and IR and NMR, and in this way you will able to definitely solve the problem. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us this productive session. And friends, we are going to give you more of information on mass spectroscopy and problems of spectroscopy. Friends, you're requested to be with us as we are going to be back after a short break. Hello friends, welcome back to this session where we are discussing on mass spectroscopy, and we are taking some problems of spectroscopy too. And for the discussion on the topic, we have with us in our studios Dr. Vandana. Dr. Vandana is continuously giving us in-depth knowledge on the topic. So we would like to welcome our guest Dr. Vandana once again. Hello ma'am, welcome.
Thank you so much ma'am. Hello viewers, once again we are going to discuss more and more about this spectroscopic problem. Here is another problem you can see. Let us see the data first. A organic compound contains 66.6% carbon, 11.1 hydrogen. In ultraviolet, it gave a characteristic band at a value of 275 mu, and epsilon maximum is 17. This is as far as UV data is concerned. Now another data, that is infrared IR bands are at a value of 2941 to 2857 centimeter inverse, medium, and a strong peak at a value of 1715, and another medium peak at a value of 1460 centimeter inverse. In NMR's 3 singlet peak appears at a value of 7.52 quartet. For 2 hydrogen, you can see in the within bracket hydrogens, the number of hydrogens are also given. Another singlet peak is there at a value of 7.88 tau for 3 hydrogens. And this is another signal 8.93 tau, it will be a triplet, and it is for 3 hydrogen. Now let us see how will we proceed. First of all, we can calculate, you have studied how can we calculate the empirical formula. When we having the particular percentage of elements, oxygen you can calculate, you know it very well, you can calculate by minus all the carbon percentage and the hydrogen percentage. So the empirical formula comes out to be C4H6O. So now we have molecular formula of a particular compound. The absorption at this value specifically immediately gives an idea that there should be a possibility of carbonyl group. This is the value 275 millimicron. Due to N2 pi star, you know this is what is this? This is the transition involved arises due to the carbonyl group when non-bonding electrons are also there on oxygen atom. So this is N2 pi star transition. The absorption at a value of this medium in the IR spectrum is due to the carbon hydrogen stretching, and this value 1500 it should immediately attract you. If this kind of range is available in the spectrum, it immediately gives you an idea whether it is a carbonyl group, aldehyde group or ketonic group. This higher peak will show that it can be a ketonic group, that is saturated ketonic group, and this value may be due to the carbon hydrogen bending. The NMR spectrum reveals 3 kinds of proton. Number 1, 8.93 for 3 hydrogen, that is triplet, quartet at this value. So we can see CH3, it will have a triplet at a value of 8.93, and this will because of multiplicity, because 3 hydrogen there are, so it will absorb at a quartet. This proton will absorb at quarter and these proton absorb at a triplet. The singlet at 7.88 values due to the methyl group adjacent to the carbonyl group. Hence the probable structure of the compound can be CH3, CH2, COCH3, because this CH3 molecule will not split, that is it is observing at singlet, so it should be like that, there should be no adjacent hydrogen atom. Immediately you can have an idea that when it is a singlet of 3 hydrogens, it will be nearby have no hydrogen atom. And the double bond equivalents you can calculate because oxygen divalent is there, so we can calculate in this way, and it is comes out 1. Another problem is there, an organic compound with molecular mass 69 is transparent above 200 nanometer. The absorption bands for infrared spectrum are 2941 centimeter inverse. A medium peaks are there at a value of 2273, at a value of 1460, and what NMR says, it says that there are 2 signals. One is septet at a value of 7.28 tau, and you can see the coupling constant value also. Another doublet 8.67 tau. So first of all, what kind of 2 absorption bonds at a septet and a doublet? The same values of coupling constants suggest the presence of this kind of pattern. These proton absorb the doublet due to this proton because 1 proton is there. So 1 plus 1, if you remember the n plus 1 rule, n is the number of hydrogen. If there is 1 hydrogen, so it will absorb a doublet, and there are 6 hydrogen, so it will absorb a septate. So this should be the part of a structure, and this amounts lead to 40 through mass unit. If you calculate the mass, total mass of these this moiety, the remaining 26 mass unit correspond to C triple bond N stretching. Thus the structure of compound under examination should be like this. The ratio in the 2 sets of proton is 1:6, which is in accordance with the given data. Also a proton septate slightly downfield is due to this proton septate. It is in downfield because of the presence of this C triple bond, that is cyanide group, directly linked to this proton. So it will observe at downfield as compared to these proton because these are not surrounded by this kind of moiety. The singlet at a value of 2941, and this correspond to CH stretching and carbon-carbon stretching for at a value of 1460. So in this way you can calculate this structure. Another problem is there. If a hydrocarbon containing 85.7 carbon, 14.3 hydrogen and is transparent above 210 in the ultraviolet spectrum, As far as infrared spectrum is concerned, there are the 3 peaks you can observe over here, 3022 centimeter inverse at a value of, and another value 1676. This M shows that medium, not very strong peak, medium peak. Another peak is there, 965 centimeter inverse. As far as NMR spectrum is concerned, here you can see 2 singlet, that is 2 peaks are there but singlet. At a value of 8.40, doublet and 4.45 quartet in the integral ratio 3:1. The empirical formula from this calculation, that is from carbon and hydrogen, it comes out to be this. How can you calculate oxygen? Simply if we minus this percentage from 100, if it comes out 0, you can see this is the 100. So no oxygen atom will be there. If some difference is there, then obviously oxygen can be there. Since the ultraviolet spectrum is transparent, it shows the absence of conjugation. So you can see immediately we have an idea that if this shows the transparent value above this, it will show that there is absence of conjugation. You know what is conjugation? Conjugation is nothing but alternate single or double bond and carbonyl group also. From IR, these values shows that aromatic compound, or we can say another double bond CH type of compound. Since carbonyl group is absent, we have seen from UV visible spectra, hydrocarbon must be unsaturated, because when carbonyl group is not there, so where is the possibility? Of course, from the hydrocarbon. Now let us see the NMR. 2 signals are observed. The doublet at this value must be a methyl group attached to this moiety, that is CH double bond. The second signal, due to the 1 proton quartet, appears downfield at a value of 4.45, and it must be due to deshielding. So it will observe a doublet and it will observe a quartet because of these 3 hydrogen, and it must be due to deshielding by the presence of double bond. These proton will observe at downfield because of this double bond. Molecular formula is exactly double of it. If we see the molecular formula, we have to calculate at every point what is the molecular formula of the identified moiety and what is the molecular formula left for the unidentified moiety. So you should have all points open. Then when you calculate the molecular mass of this moiety, the molecular formula is exactly double of it. Hence the probable structure of the compound can be like this. So you will able to calculate the structure of the compound. In infrared spectrum, at a band at a value of 965 is characteristic of an alkene in which hydrogen atoms are trans. So this molecule you can write as a trans moiety, not as a cis. So immediately you will get the idea from this peak that whether the molecule is cis or trans as far as double bond is concerned. Another problem is there. A compound with molecular mass 71 is transparent in the ultraviolet spectrum. In infrared, there are 2 peaks at a value of 2941 to 2857 at a value of 1460. As far as NMR spectrum is concerned, there are 2 signals formed at R 1.78 tau, this squares, and 6.5 tau. 2 sets of proton are in ratio when we see this value 16.8 and 23.9. We can calculate the ratio of the protons, and it should come out, it is come out 2:3. Thus CH3 and CH2 may be the part of this structure. The carbon atom carrying their 2 sets of proton cannot be directly linked, otherwise splitting of the singlet into multiplets would result. Hope you understood this. What I am saying, that if they are connected to each other, that is CH3 and CH2, so it should appear as a quartet and it should appear as a triplet. But you see there are 2 singlets observed. This will also give a singlet, this will also observe a singlets. So these are separated by some moiety. Let us see what is that. An absorption band at a value of 2247 should be due to this carbon triple bond knife, this is cyanide group stretching, which is also in accordance with the odd molecular mass of the compound. We have already told you in the mass spectrum that if a molecular formula is odd, that presence of nitrogen should be odd in number. Thus the unit CH2, CH3 and these are identified in this way. and it leads to the molecular formula, or we can say if we calculate the mass, it comes out to be 55. So remaining 16 mass unit corresponding to an atom of oxygen. Thus the probable structure, we have already told you that these CH3 and CH2 should be connected by a different atom, and here you can see this sign of the probable structure can be possible. The two proton singlets appear slightly downfield, being surrounded by oxygen and cyanide group on the either side. So you can calculate CH2 present over here or here. It shows downfield, so definitely it should present in between oxygen and this cyanide group. The absorption peak we have discussed many times in the previous discussion or previous problem, that these values 2941 to 2857 and 1460 corresponded to carbon hydrogen stretching and carbon carbon stretching respectively. So this is how you can calculate the possible formula, possible structure of the compound. Let us see another example. An organic compound with molecular formula 72. So we have important information over here, molecular mass, and this is the information for UV visible spectrum, that is 274 nanometer and epsilon maximum is 17. In infrared, a strong absorption band is absorbed at a value of 1715 centimeter inverse, and medium absorption bands are formed at a value of 2941 to 2857 and 1460 also. As far as NMR signals are concerned, the signals in the nuclear magnetic resonance spectrum are at a value of 7.52 tau quartet, not quarter, it should be quartet, at a value of G, you can see the value of J 7.3 and 12 squares, that is you can calculate the ratio of the proton also with these squares values of different peaks of NMR. Another value here 7.88 as a singlet. So we have 3 peaks from NMR, triplet, singlet and quartet. The NMR spectrum a quartet, a triplet with the same value of coupling constant. You can see same value of coupling constant having proton ratio 2:3 suggests then this should be the part of the structure. The 3 set of protons are in the ratio of, if we calculate by these squares value, that is coupling constant, this should come in the ratio of 2:3:3. A 3 proton singlet may be due to CH3 group, and this amounts all this concluded to 44 mass unit. The remaining 28, if we minus this value 44 from this molecular mass of a compound, we have this value, remaining value 28, and if we link this, it can link easily to the carbonyl group. Here you can see the signals also, significant signal also is there in the infrared, which immediately give you an idea what kind of function group is there. The presence of carbonyl group can be confirmed by this value due to carbon double bond oxygen stretching. It is further confirmed from the ultraviolet spectrum, which shows a band at a value of 274 nanometer with a low extinction coefficient, that is we have seen it was 17 if I am not wrong, and it is the result due to this value is result due to the N to pi star transition. The absorption band at these values thus related to these values, that is this value is related to carbon hydrogen stretching, we have told you, and 1460 value related to carbon carbon stretching. So by calculation all these data, the structure comes out to this. It will observe a triplet, these kind of proton observed at a triplet due to this 2 proton n plus 1 rule if we apply, and this moiety, that is CH3 will observe at a singlet because no adjacent proton is there. So no multiplicity will observe, no splitting will observe over here. How can you calculate this kind of moiety is related to this? Because of downfield value of the adjacent proton. Another value is there, a compound with molecular weight 116 gave the following spectral information. Here is the ultraviolet visible data, that is a value of 283 millimicron at a epsilon maximum 22, that is low value. Here you can see this is the low value. I have discussed all these points, whether this value shows what kind of indication it shows in the ultraviolet. If you have any doubt regarding these values, how can we have an immediately idea? So you go through the ultraviolet visible spectroscopy first, what kind of transitions we have discussed, what kind of bands, absorption bands we have discussed. We have discussed all the bathochromic, hypsochromic, hyperchromic, and all the ifs and buts. We have discussed it, that if the value is low, what should be there, if the value is high, what should be there. As far as IR data is concerned, you can see at a value of 3000 to 2500 centimeter inverse, another peak is here at a value of 1715 centimeter inverse at a value of 1342. It is a W indicates the weak band. NMR signals shows a singlet at a value of 7.88 tau for 3 hydrogens. This hydrogens is particularly about this moiety 7.40. This multiplicity shows the proton at the adjacent carbon atom, triplet shows the number of proton at adjacent carbon atom, and 2 hydrogen shows the hydrogen atom of this particular moiety. Another singlet, another signal is there 7.75 tau. A triplet is there because of 2 proton, and another signal is there minus. You can see the value is minus in minus 1.1 tau singlet due to 1 hydrogen. So let us discuss it one by one, all the values. In the ultraviolet spectrum, this value of low intensity indicates the presence of carbonyl group. We have discussed in earlier problem that value was 275, now you can see 283. So you should have an idea. The presence of carbonyl group further confirmed by a strong band at a value of 1715 centimeter inverse. A very broad band at a value of 3000 to 2500, that is 2500, is the most characteristic of the acid. You know what is acid? This is nothing but RCOOH, and this OH stretching will give you immediately avidya, and it appears as a result of a strong hydrogen investigation. It contains carbonyl group as far as these two informations are concerned, and due to this data we can conclude that it should contain carboxylic group also. Further, 2 triplets results at a value of 7.4 tau having the same integral area. It must be due to CH2 moiety. Clearly, 2 methylene groups must be under different environments, thus coupled to give rise to 2 triplets. Here you can see that this moiety CH3 is due to 7.88, is a methyl group attached to the carbonyl group. Why I am saying it is attached to carbonyl group? Because here no doubt 3 hydrogens are present, but still it is a singlet, because in adjacent carbon there is no hydrogen, so it will appear as a singlet. Here you can see CH2, this is triplet. It will not give the NMR spectrum, this is wrong. It will give you a triplet because of presence of, it will gives you a singlet. So these are the data, it will gives you singlet, it will gives you triplet. Another problem is there. If an organic compound with molecular mass 88 absorbs at a value of 206 nanometer, epsilon maximum 50. Here you can see some a little bit more value of epsilon maximum. In infrared medium, these are the peaks. Also strong absorption band is formed at a value of 1736 centimeter inverse. And these are the values or signals observed in NMR spectrum at a value of 1.93 tau singlet. These are the J value, 5.88 for triplet, 8.33 sextet, 9.05 triplet. So as far as these J value is concerned, we can calculate the ratio of proton, that is 1:2:2:3. The formation of a triplet and a sextet and a triplet with the same value of coupling constant, that is 7, 7 and 7, shows that this can be a part, this moiety can be a part structure, can be a part of a structure even if one proton singlet at very low field suggests as CH also as a part of a structure. This amount leads to the 56 mass unit out of 88. The remaining 32 mass unit shows the presence of 2 oxygen atoms. The formation of a strong absorption band at this value from the IR spectra shows the presence of an ester. The medium bands at these values are due to the carbon-hydrogen stretching, carbon-carbon stretching, or we can say carbon-oxygen stretching respectively. Thus, the most probable structure of the compound is like this. It cannot be this. Why? How it cannot be like this? Because here one oxygen atom must be there. I missed it with double bond, that is this kind of carboxylic group and this kind of carboxylic group. Because in such a case, carbonyl stretching for acid would appear at this or below. However, we observed higher values. An absorption band at this and this will not give any definite information, but from this value we can conclude that the structure of the probable structure must be this, not this, because of the downfield value. Another problem is here, a compound with molecular mass 104 is transparent below 210 nanometer. The infrared spectrum you can see observed at these values. Another weak bands he is talking about at value of 2695 centimeter inverse. As far as NMR spectrum is concerned, you can see the peaks minus. So minus peaks immediately give you idea. At a value of 0.95 tau, it is a singlet. 5.4 is the J value, 5.87 tau singlet. So singlet, singlet, quartet and triplet. From this value, that is J value, you can calculate the set of protons, the ratio of the protons 1:2:3 from these values 5.4, 10.6, 11.2, 16.2. So the ratio can be 1:2:2:3. A quartet and a triplet with the same value of coupling constant, that is 7.1, 7.1, shows that this can be a moiety. A 2 proton singlet means a CH2 group. A singlet with the negative value, we have observed in the previous case also, the negative value immediately gives an idea that there should be a carboxylic group. And when we calculate the total mass of these moieties, it comes out to be 88 apart from 104. So 16 mass is remaining, and which is correspond to oxygen atom. So from the NMR signals, you can calculate that how can we connect this moiety to each other. It will be a triplet, it will be a quartet, it will be a triplet, it will be a singlet. So in this structure, the set of protons appears downfield C. How can you say that this kind of proton should be there? Because of the downfield or high field. At a band of these values, they are not giving any information from, but from the sometimes you will be confused by the data. So first of all, you need to focus on the significant data and try to calculate the structure of the compound slowly by calculating the number of proton first, and not confusing by the this kind of data, because you can see this kind of data do not give any definite information. So do not indulge with the first information if it is given in the problem. Let us go through all the data first of all, and then pick out the significant values, whether it is given in the UV visible spectrum, NMR, IR or NMR. Another problem is here, a pale yellow compound is slightly acidic in nature and gave the following data. So these are the values UV, IR, and you can see these value indicates the presence of conjugation, some benzenoid compound. Benzene ring may carry some groups which causes bathochromic and hypochromic shift, and these value due to this group and due to NH stretching. So by elucidating the structure all these data, we come to conclude that this should be the compound. Let us discuss this problem in the forthcoming lectures, because it requires more time. So friends, you can easily calculate the structure of the compound if you keep all the points in the mind, that what are the significant characteristic of UV visible spectrum, IR spectrum, NMR spectrum, and mass spectrum. Hope you understood this. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us this productive session. Friends, we will be meeting again very soon and would be discussing more. So you are requested to watch us, to write us at info.cec@nic.in. Thank you, ma'am. Thank you once again.
Thank you so much.